Hello, welcome back to Chem 161. We are almost at the end of the week, and it is good because the weekend is almost here, and I really want to do anything other than grading, which I'm still not done with, but I believe I'm done with your labs, and I uploaded those. If I didn't, I need to do that. So your lab score should be posted for lab number 1. And other administrative stuff to talk about. So there was talk in the class Discord about when our quiz scores released. So the quiz number 2, since it's currently still due, it's due tonight and closes tomorrow. Those scores aren't available until the quiz is closed. And then I have to manually go in and open the quiz. So if the quiz scores haven't been released by Saturday, please remind me. I will go in and hit a button so that you can see your scores. You should also be able to see your results because when I unlock it and I check a box, I release all the answers, and you should be able to go in and see what your answers were compared to the correct answers in the assignments tab. Lab worksheet number 2 is going to be due Wednesday, May 4th. Let me open something really quickly. Let's see here. What is your lab number 2 about? Is there anything I really need to talk about in lab number 2? So, lab number 2 is basically all of the stuff that we've done in chapter 6. And it is a summary of some experiments that we did in 140 at the end. So, it should be pretty straightforward. I don't think that there's much that I need to really talk about here. But you can read the documentation, watch the videos, and then ask me any questions you might have in the Discord or email. Important, nobody, I think, ran into this problem, but it's worth mentioning anyway, that at the bottom of the Excel spreadsheet are tabs. Make sure that you are answering all the questions in all the tabs and not just the first one. Yeah, that's all I can think about for the lab. So the labs are kind of just tacked onto the class because it's an online class, and I don't have another period to do a lab discussion anymore. They stopped letting me do that because they didn't want me to book 3 days in the course schedule. So yeah, if you have questions, we're gonna reserve the lab questions to the Discord, so just let me know there or by email if you have any questions about those. All right, we're going to finish chapter 6 today, hopefully. We're going to start off the lecture today by talking about dilutions. Tuesday, we did a discussion about making solutions. Oh, I'm sorry, it's 2 p.m. I'm just going to yawn all hour. I don't know what it is about 2 p.m. I get tired. On Tuesday, we talked about how to make solutions using a solid reagent, so like sodium hydroxide or KBr or whatever. And then we would add that to a container. We would then add water to it, fill it to the mark, mix for 60 seconds, and then enjoy. Here we're going to do a similar process, except that our solution has already got water in it. And if our solution is too concentrated, we need to dilute it. And so the way that you dilute a solution is by adding water to it. You just add solvent. We have a formula that is specifically for this purpose. However, it's very important that this formula is used appropriately. This is the dilution formula for dilutions only. So be mindful of this caveat. This formula looks super convenient and everybody wants to use it for everything that involves molarity and volume. Do not do that. Okay? So if you are doing stoichiometry for, like, say, a chemical reaction, do not apply M1V1 equals M2V2 to the chemical reaction. Only apply this to dilutions. So just be very mindful of that, because that is a very common pitfall to fall into in chemistry, is using this formula when you're not supposed to. So dilutions only. All right. Now, what do the terms mean? Well, if I draw a line down the middle of this equality, And then I label the sides here. Everything on the left with a 1 is going to be our stock solution. This is what you have before you do the dilution process. Oh, sorry, I'm just yawning. I'm trying to mute myself so you don't hear me going in the mic here. This is what happens when you sleep deprived all week from grading. So the stock solution is what's in the stock room. So we go into the back room. We have this in a cabinet or in a locker or whatever. And this is what we make our solutions out of. The reason that we have stock solutions that are very concentrated is so that we aren't needlessly shipping water around. Water is heavy. And to transport water requires logistics and resources, so we'd have to expend fuel to transport the mass of water. But water is also abundant, relatively speaking. There's water everywhere. You can make a solution in your lab by adding water to it that you have, right? We have a distilled water device in the laboratory at Everett Community College. Other colleges might have deionized filters where they can pass water through it. And so you just open a spigot and the water comes out, and the water is perfectly suitable for chemical reactions. That being said, stock solutions are often too concentrated for the applications that we want to use them for, and so we need to do this process. M is molarity. That's the concentration of whatever side of the equation you're looking at. So M1 would be the stock solution's molarity. M2 would be the diluted solution's molarity. V is the volume. On the stock solution side, the volume is going to be how much stock solution is necessary to do the thing that you want to do. On the dilute solution side, V2 is the volume of the solution you're trying to prepare. Generally speaking, you choose these when working with this equation, and then this is printed on the bottle when you buy it or you order it from whatever supplier sends it to you. The end result is that you need to solve for this. So this is the general procedure for doing any dilution. Choose what molarity and volume you want to make. And then based on the stock solution's molarity, you calculate the volume of stock solution that is necessary to do the dilution. All right. This should all be review from Chem 140. Here is just all of that written out on the slide here. So let's do an example. So I want to make this solution, and I have 10 molar calcium chloride in the stockroom. What is the procedure that we should follow to prepare this solution for use in the lab? So the first thing that we need to do, I gotta set the PowerPoint or the Photoshop up here, is I can't see my numbers because I had a window in the way. I need to write down the formula. And I need to identify what I have. So I'm going to do something like this. So I know that 1 is the stock side and 2 is the dilute side. So what is my stock solution concentration? So that's 10 moles per liter. And I know the dilute concentration is 0.500 moles per liter. And I want to make 3 liters of that solution. I don't know how much I need to use, because the equation needs to be solved. So I'm just going to write the variable there. And now I know that this is what I need to solve for in my equation. So we'll solve the equation for V1. And so we'll plug in the numbers now. So M2 is 0.500. Sorry, my Photoshop is really chugging today, so I'm going to lose a few pen strokes here and there. Divided by the molarity. Try that again. The molarity of the stock solution. You'll notice the units cancel out to give us volume, which is what we're solving for, so that's good. And we'll come over here to the calculator. So when I type this equation into the calculator, the result I get is 150 milliliters of stock solution. So once you've calculated the volume that you need, you then follow the same procedure that you would if you were preparing with a solid, but instead you're going to add the liquid reagent. So to prepare our dilution... Oh my goodness, I hate this today. We would do the same three-step process. So step 1 would be to add 150 milliliters of the stock solution, which was 10 molar calcium. Calcium chloride. 2A. What size flask do we need? We needed 3 liters, so we'll say 3-liter flask. And then once we have done that, step 2 would be to add H2O to the fill mark. And then step 3 would be to mix for 60 seconds. And of course, step 4, enjoy. All right, so again, same calculation that we're doing, or I'm sorry, same procedure that we're doing for the preparation of a solution with a solid reagent. It's just the calculation is done differently because we have a solution already that we are diluting. All right, we got a picture of that on the next slide here. And that looks like this. Now, an interesting consequence, we'll come back to this picture in a second here, is that if I plug in all the known numbers down here, remember that M times V equals moles, right? So if I multiply these together, I get the same number of moles on both sides. And that should make sense because the only difference between before and after in a dilution is just water, right? I am changing the amount of solvent in the solution. But the number of moles of solute is always the same before and after because it is not being added. So in reality, what this calculation we're using does is tells us the number of moles that should be taken from the stock solution to be used in our dilute solution. Now, when I gotta zoom out here. When I do this dilution, again, the same sort of idea of make sure that you get all of the solute applies. So when I'm adding water to this, you also want to rinse this one out too. Make sure that it is good and clean, that all of the solute has gotten transferred. Otherwise, you'll get a solution that does not have the appropriate concentration. And then you want to fill it to the fill mark with the meniscus touching the line, just as before. All right. You'll get practice with this in 162. So let's do another example here. So I want you to make 1 liter of 1 molar HCl, but all I have in the stockroom is 14 molar HCl, because this is what it's sold as. It's sold as concentrated HCl. How do I make this solution? So what I want you to do is first yawn and get it out of your system, I guess. Secondly, I want you to figure out which variable in the dilution formula you're going to solve for. Hint, it's the same one. Then write out the procedure using the result from a calculation for the preparation of this solution. So you should have 3 steps. The 4th step is to enjoy. It's optional. I know some of us don't enjoy making solutions or well, anything, really. So go ahead and do that calculation. We'll go over the answer in about 3 or 4 minutes once you've typed something in the chat. So see you in a bit. One more minute, we'll go over the answers. All right, let's go over the answer here. Where is my... There it is. Okay. I should be doing everything I can to stay out of Photoshop because I didn't reboot my computer. But here we are. All right. So you don't have to make this table. I just make this table to organize the information in the problem. All right, so there's our concentrated solution is 14 molar. And I want 1 molar HCl. And I want 1 liter of it. So that means that our volume of stock solution would be this result, which will be 1 molar times 1 liter divided by 14 moles per liter. Those cancel out. We'll go over here. So 1 times 1 is 1 divided by 14. Now, you can use your answer in either milliliters or liters. I just think milliliters is easier to measure out when it's smaller because graduated cylinders up to like a liter exist. I mean, you could have any graduated cylinder, any size. So now that we've got this, we're going to take that volume, so 71.4 milliliters of our stock solution, and add that to a 1 liter flask. And then step 2, we're going to add H2O to the mark. Oh my goodness. We're going to mix it for 60 seconds and then, of course, enjoy. All right. Any questions, let me know. All right. I have another one of these. I have 2 of these, actually. Let's see here. The first problem is actually different than the second problem. So I'm going to do the first problem for you. I'll leave the second problem because it's just another dilution. But go ahead and try both of these problems. We'll go over the answers in just a little bit. Say 5 minutes or so. One more minute, we'll go over the answers. All right, let's go over the answers to these problems. So I got to go over here. Oh, that's perfect. Look at that. All right. Now, this problem is slightly different in the sense that if you make your little matrix here, you'll notice that I have a 15 molar solution of sodium hydroxide, and I'm starting with 0.2 liters of it. And I want a 3 molar solution at the end, but I don't know what its final volume will be. So in reality, you could use this formula to do any number of questions, but the most common one by far is the dilution formula. Or the dilution process. It's called the dilution formula. So when you are solving for an amount to use to prepare a dilution, you're going to be solving for V1. But I could ask you any question that makes you solve for any one of these variables. So identifying the context of the problem is essential. So V2 will just be M1 V1 over M2, which would be 15 moles per liter times 3. Oops, that's not right. Sorry, hold on. 15 moles per liter times 0.200 liters over 3 moles per liter. 15 divided by 3 is 5. 5 times 0.2 is 1 liter. So if I had 200 milliliters of a 15 molar sodium hydroxide solution, and I diluted it to a total volume of 1 liter, it would then have a molarity of 3 moles per liter. So that's the first problem. And then the second problem, what volume of sodium nitrate 6 molar solution should be used to make a solution of those specifications? So again, we'll just do this. So here is the starting molarity, and I want 1.20 moles per liter, and I need 525 milliliters. So I can solve for that. Which would be 1.20 moles per liter times 0.525 liters over there we go. And I don't know what that is off the top of my head, so 1.20 0.525 divided by 6.00 equals there you go. All right. It didn't ask us to describe how to prepare the solution, so we don't have to do that. All right. Any questions, let me know. Let me check something real quick. Now, we'll start this next topic when we come back from the break. So I'm going to do the break a little bit early because I need to go, like, eat a banana or something because I'm just falling asleep here. So let's take our break slightly early. We might end class a little bit early today, too, because we just need to finish Chapter 6, and then I will briefly start Chapter 3 a little bit, but we won't get into anything crazy nitty-gritty. We'll do that next week. So where's my timer? There it is. I'll start the timer, get the music going, and I'll see you in a little bit. Alright, we're back. I've eaten a banana. I went and pet a cat. I got more water. Hopefully I won't fall asleep again. Not fall asleep as in, like, I've fallen asleep during the lecture, but I'm just yawning all the time, so. See, it happens to instructors, too. It's not just you guys falling asleep during my lectures. I fall asleep during my own lectures. Alright. The rest of Chapter 6 is talks about different ways to express concentration. So molarity is not the only way that we express concentration in the sciences. In chemistry, it's by far the most common one. But in other places, such as healthcare, for example, molarity isn't something that people really work with in the nursing profession. They work with different units that are more practical, such as mass volume percentage for, say, saline solution that you would administer through IV. And the reason that they do that is because it's much less time intensive to write out a procedure of measure this many grams divided by this much volume, when grams and volume are much more common units that we have, like, say, a balance to measure, rather than have the nurse do the calculation from grams to moles or moles to grams or whatever every single time. So we're going to look at some of these other concentration expressions here, and we'll talk a little bit about various applications that they can be used in. So the first one's mass percentage. We've already done mass percentage. We did this earlier on when we were talking about, what's the mass of the component divided by the total in the formula or whatever. Well, you could do that for mass percent of a solution. And so typically this is referred to like whatever solute is in there divided by whatever the solution's mass is. If you have multiple solutes, you can pick one. You could also pick all of them. It's kind of up to you. An example that I came up with when I was writing these slides was that if you buy sodium hypochlorite solution, also known as bleach, the formula on the bottle says that it is 7.4% by mass. And so what that means is that if you pour out some bleach into a beaker, and the amount that you pour has a mass of 100 grams, in that 100 grams, you'll have 7.4 grams of the active ingredient of bleach, sodium hypochlorite. All right. So let's do an example. What is the mass percentage of HCl in a solution that has this molarity? Here's its density. So I'm giving you a bunch of units here. And the reason for this is because we're going to need the components of mass percentage in order to answer this problem. And so we're going to need all sorts of different things here. So let's do an example. Oops. Bonked my water. I almost knocked it over. All right, so let's write out the formula for mass percentage. Oh, great. My percentage only got the dots. There we go. So what we need is we need to know the mass of the solute, and we need to know the mass of the solution. So what I'm going to do is, in order to get the masses of these, I need to pick some amount, right? I can pick any amount. I'm going to pick a really simple amount. I'm going to pick 1 liter. You can pick any number you want, but if I have 1 liter, and I do this, I multiply by the molarity, I would then know how many moles of solute, or HCl, are in there, right? And then what I could do is I could say, well, I want the mass of the solute up here, yeah? So this needs a mass. This is moles. So let's turn it into a mass. And that's going to mean I need to go to Lentech to get the molar mass of HCl, which I believe is 36.4 something. 36.46, so. So 1.150, 36.46. So this number would be the mass of solute. In my 1 liter sample, I have 5.47 grams of HCl. Now, what about the mass of the solution? Well, if I still have 1 liter of solution, what would the density tell me? Well, this would tell me that first I got to turn liters into milliliters. So we'll do that. And then I know that the solution has a density of 1.19 grams per milliliter. So this would tell me the mass of the solution because it is both the water component and the HCl component. So 1 divided by 10 to the minus 3 is 1,000 times 1.19. So my total solution mass is, oops, not point, 1,190 grams. And that'd be the mass of the solution. So you could see that we're going to have to use the different units that are available in different ways. Because now I just take these numbers and I plug them in up here, right? And we'll just do this in blue. And so I get 5.47 over 1190 times 100. So this solution should be 0.460% HCl by mass. And look at that. That's what we get. All right. Volume percentage is used in the exact same way, except instead of mass, you use volume. Now, if you have a solute that is a solid, this is not super helpful to you. But if you have a solute that is a liquid, for example, if you have, like, say, ethanol in water, then volume percent is much more useful to you. Now, there is an issue that arises, and the issue is probably not one that you're expecting. This is not the volume of the solute plus the solvent. If your solute and solvent are of different substances, so they are not like an aqueous solution plus an aqueous solution, the volumes don't add together. And to show that, I have this video. So this is going to be a video of adding water to ethanol. Yes, my browser's up to date. For fuck's sake, YouTube. Stop it. Sorry, I'm clicking on this, and it's just making 74 windows that say, your browser's up to date, and I don't know why the 4th one today worked, but let me close all these. All right, so there's our video. Let's get this on the screen here. All right, this is a very interesting video because a lot of people don't know this or even expect it. So we're going to hit play on this. And I have it muted because I'm going to talk over him. All right. So this guy is Gross. No, literally, that's his name. His name is George Gross. I like to make that joke. I feel bad. I've never met this guy. What George is going to do here is he's going to mix these two solutions together. Now, the solutions have been indicated with just dye. So we've put yellow food coloring into the water and blue food coloring into the ethanol. Might be vice versa. I don't know. One or the other. When you mix them together, we should get the expected color, which is green. So now, the way that a volumetric flask works is that there is a fill line on the flask. And so you could see it kind of right here on this other flask. When you get the meniscus on the touching the top of that line, the flask is full. And you could see the other one on this flask here, and there is another one that's here. It's just harder to see. So he's going to fill these properly. There it is. You can see it now. And this takes a second to do, so we're going to just fast forward through it. There we go. He's done. Oh, no, he's not. But you can tell he's being very careful. He's like adding a drop at a time. Okay. Now he's going to do the same thing with the ethanol, and so we don't need to see them do this. There we go. That's done. Each of those flasks has a volume of 500.0 milliliters. Volumetric flasks have very specific volumes. Now, in theory, two 500s would equal 1,000, and this flask has 1,000.0 milliliters of volume. So that's what we're going to do. We're going to add this to the flask, and it's going to take a second. There we go. Pause. I paused a little too slow. So you can see that this flask is essentially empty. Like, there's obviously going to be some stuff in here, but I wouldn't say more than a milliliter. And I'm just going to go frame by frame here. So you can see that there's not anything that's in that flask. And when he sets it down, that anything that it looks like is in there was just the reflection of the surface there. So, totally empty. All 500 milliliters have been transferred. We're going to transfer the next 500 here. And 500 plus 500 should equal 1,000. But as we're going to see, there's an issue. Now, the solutions are being mixed together. Yellow plus blue does make green, so we have combined them. They are not reacting. Ethanol and water do not react with each other. And there we go. So you're going to look at the second solution here. Also totally empty, so all the liquid was transferred, essentially all of it. But when we put the flask down and we look at where it lines up here, he's like some 20 to 50 milliliters short. So when we added these volumes together, we didn't get anywhere close to the correct volume. Now, what's the deal here? Now, and for some reason, I don't have this slide in my presentation here, and I really wish I did. I need to actually put it in here. But it's in a different set of slides, and I can't ever find this picture again, so I need to go find these slides real quick. I believe it's in here. Let me find the slide that I want. Yeah, there we go. Okay, so hold on just a second here. I'm going to close this, and then this is going to go away. And then this will appear from a different class here. And so this is really what I wanted, was just this picture here. The beaker on the left, or actually the mason jar, is very obviously full of golf balls. But is it full, like underline full? And the answer is no. There's little gaps between all of the golf balls here, right? So I could put, like, say, this coarse stone granules into here, and those granules would fill in the gaps between all of the golf balls. The whole thing still has the same volume. It's the volume of the jar, but we're just being more efficient with how we've used the space, right? With molecules, it's the same idea. The big molecules will have gaps in them. Gaps that are large enough that smaller molecules can then fit in those spaces. In the case of ethanol and water, ethanol would be the golf balls here, and water would be the little tiny chips of stone that are fitting in between it. Since ethanol already has claimed that volume as ethanol's volume in the 500 milliliters, the water that mixes in there is going to occupy some of those spaces between the molecules, and thus it will be a part of the 500 milliliters that has already been attributed to ethanol. The remainder of the water will just do whatever water does for its volume. But the point is, by mixing things of different sizes, you get a volume that is smaller than you would have expected because of filling in the gaps like this. All right, so let's close that real quick. We'll go back to our slides. Oops, I got to find the right slide here. There we go. So the takeaway here is that you cannot add volumes together. The volume of the solution must be given for a volume percent problem. If you don't have that number, you can't solve the problem. Or you have to do it experimentally and go get the number yourself. All right. So keep that in mind if you're ever given a volume percent problem. Don't just add your volumes together because you will generate a lot of error that way. All right. Let's suppose you have half a liter of nail polish remover. If half of a liter is 60 per, or if half of a liter, gosh, I'm just brain dead today. Sorry. If you have half a liter of acetone, let me start over. If you have half a liter of nail polish remover and that nail polish remover is 60% acetone by volume, what mass is in your container? Now you'll notice that I'm asking you for mass here, even though I gave you a percent by volume. So in order to deal with this, you have to have a density. So I'm going to let you play around with this for a bit. I want you to follow the same strategy that we did for the mass percentage problem, which is write out the formula, find what things you know, and then use that information to solve the problem as given. We'll go over the answer in about 3 or 4 minutes. One more minute, we'll go over the answer. All right. So let's go over here. Make that a little smaller so I can fit this. Okay. So let's write out the formula for percent by volume. Actually, I guess at this point, the solute would not be the acetone here because it's most of the solution. So let's just write acetone here. Times 100%. All right, so I know what my percent volume is. It's 60.0. And I know the volume of the solution, so I need to figure out the volume of acetone here, right? So if I say the percentage of the solution divided by 100% times the volume of the solution, that would be the volume of acetone. And so that would be, so 60.0% divided by 100% times the volume of the solution. So my percentages cancel out. And that would be, so 300 milliliters and this would be acetone, which I can then multiply by the density. .784. And I get 235.2, which 3 sig figs is just 235. Which is what you all got, and that's great. And so it is going to be a lot, but the reason that it is a lot is because 60% of the solution is acetone, so it's going to make up a significant part of the solution. All right. All right, the last formula, very similar to the others, except for we have the mass on the top and the volume on the bottom. There is actually an important caveat to this formula, and that is this. When we're doing mass volume percentage, by definition, for this formula to be valid, we use the mass in grams and the volume in milliliters. Now, you've actually used the mass volume percentage already. in this class. You use this to determine the percentage of sugar that was in a soda can. And so in order to find the percentage of sugar, we had you take the mass of sugar, which you got off the label, and divide by the volume of the can, and then multiply by 100%. That gave you a percentage. So mass volume percentage is used in various applications, like determining sugar solutions, or what the concentration of a saline solution would be for IV, so on and so forth. You'll notice that these units don't cancel out. They just sort of mysteriously disappear. We're going to talk about why this is more when we get to like 162 and 163, how reference solutions are used in order to make units just vanish for our purposes. But for our purposes now, don't worry about that too much. Just ignore the grams and the milliliters once you get to the percentage part. I know I feel uncomfortable saying that myself because I'm a stickler for units, and this is just how this formula is used. These last two formulas are based off of the mass percentage formula, but instead of multiplying by 100%, we multiply by these extra terms at the end. Parts per million and parts per billion, and the appropriate number. Parts per million and parts per billion are useful for situations where you have very, very, very little solute. For instance, if I'm measuring atmospheric CO2 concentration of CO2 is measured in parts per million because you take a million air molecules, and of those million, some small number that is rapidly increasing, as I say this, is CO2. It's not large enough for a percentage, at least not yet. So parts per million, parts per billion are useful for those applications. Water quality is often expressed in parts per billion. For example, if you have lead contamination, which is what happened in Flint, Michigan for many, many years, the concentration of lead in the water there was expressed in parts per billion. There is an EPA, Environmental Protection Agency, limit set to things like that, and that limit is expressed in parts per billion as well. So we're going to do some problems for this using parts per million, parts per billion, and they're all going to be environmental sounding. So here's the first one. We fluorinate drinking water because it is useful for teeth. Fluoride is very good to produce healthy tooth enamel. It strengthens it by replacing the hydroxide in the hydroxyapatite, which is not something that sounds like you should be eating it, but it's called that because that's the mineral that is formed in your teeth, in your tooth enamel. Fluoride is great for that purpose, but fluoride is terrible for all other purposes. In fact, fluoride is toxic. Sodium fluoride in your toothpaste, if you go look on the back of your toothpaste, it'll tell you, do not eat. If you swallow this, contact poison control. And the reason for that is because the fluoride ion getting in your body is not great. A little trace amount of it after you've brushed your teeth, like if you rinse out and then you swallow inevitably a little bit, probably not going to hurt you. But you don't want to have toothpaste for dinner. In fact, that's a comic. That's an interesting comic that you could read. All right, so here's our problem. The recommended limit for fluoride is 4 parts per million. How much fluoride is found in an 8 fluid ounce glass of drinking water? Here's the density of drinking water and also its volume. So what we're going to do, I got to get all this on the screen again. Same thing we did for all the other problems, really, is we're going to write out the formula. So parts per million. I don't know what I was doing there. I was just going to write parts per P, I guess, over and over and over. So mass of fluoride there we go. So there's our formula. what are the things that we know? Well, we know what the mass is, or we know what the mass of the water is, because we can get that from the volume and the density. And we know what the parts per million limit is, right? So we can write all of this out. So we'll solve for the mass of fluoride. I'm so frustrated by Photoshop right now. Let's see here. Divided by 10 to the 6 parts per million. All right, so there's our mass of fluoride. We can find the mass total by just calculating the volume times the density. So we'll do that. So the fluoride mass was, we said, 4 parts per million, so 4.0. Divided by 10 to the 6. Times the mass total. So this in the parentheses will be our mass. We have 240 milliliters times 1.0 grams per milliliter. It's going to be our mass in grams of fluoride. So that would be 4 divided by 1 times 10 to the 6 times 240 times 1. So we get 9.6 times 10 to the minus 3. I put a 3 there, I swear I did. Which, when I turn this into milligrams, would give me... Oops, hold on, that's a 4. I can't read my calculator. I was going to say, there's no way there's 9 grams of fluoride in a glass of water. Or 9 milligrams. There you go. So in a glass of drinking water, 8 fluid ounces, there is roughly 1 milligram of fluoride. And let's see what we get. Oh, that's the answer we got. Great. All right. So I have a few more of these for you on this next slide right here. Oops, I got to actually click over here. So this first one up here is parts per million of CO2. Just as a curiosity, so I wrote this slide in 2019. So Mauna Loa CO2. 2019, the number I wrote down was 410.9. What is it today? Last month. April 27th, 419.56. So within 2 years, the amount of CO2 in the atmosphere has increased by 10 parts per million. A year before that, it was 418, and 10 years ago, it was 396. So is this an issue? I mean, you're exhaling CO2, right? CO2 is a waste product. If we fill the air with CO2, what will happen? Well, obviously, you would suffocate, right? So, not great. Just food for thought. I'm not saying you should go and sell your Jeep Wrangler because you don't want to contribute to CO2, but we should probably do something about this, right? Anyway, let's assume that all of the air around you is the same as the air in Mauna Loa, which is not a good assumption. The atmosphere is very, very heterogeneous. But assuming that it is, what is the mass of CO2 found in the volume of a human breath, which is at roughly 6 liters? There's the density of air. And then the second problem, the EPA recommended limit for lead is some number of parts per billion. Let's suppose that a 300 milliliter glass of water has 4.5 micrograms of lead, and it is exactly at the EPA recommended limit. What is that limit in parts per billion? Go ahead and try these problems. This is a little more, not convoluted, but complicated, I guess we'll say. So I'm going to give you like 6 or 7 minutes to do these. Ask any questions that you might have in the chat, and we'll go over the results in just a little bit. And then we're done with chapter 6. All right, one more minute. We'll go over the answers. All right. So let's do this. And I'll just do that. There we go. Okay. So the concentration of CO2 in ppm would be the mass of CO2 over the mass total times 100%. Not 100%, sorry, that's not mass percentage. 10 to the 6 parts per million. All right, what parts of this do I know? I know what the CO2 parts per million is. It's 410.9. This is just a constant, and I know what the total mass of air is in the breath, because it'd be 6 liters times 1.225 grams per liter. That would tell me the mass of CO2 in that. So let's do that. So whatever our CO2 parts per million is over 10 to the 6 parts per million times the mass total. I'm starting to learn that if I don't lift the pen up, it doesn't do the annoying thing here. So I apologize that all my letters are going to be strung together here. All right, so there's my mass of CO2. So let's start filling in the numbers here. So I have 410.9 parts per million divided by 1,000,000 parts per million times whatever the mass total is. So we'll just say 6 liters times some number of grams per liter. And so that will give me a number of grams of CO2. So that would be 410.9 over 1,000,000 times 6 times 1.225. I shouldn't have done it this way, but that's okay. Just because sig figs are going to make me run out of space here. So that would be 3.020 milligrams of CO2. So this is not CO2 that you produce. This is CO2 that's already there. When you exhale, you are creating more CO2. And so the concentration of CO2 in parts per million will increase, as will the mass. So in 6 liters of air, there are 3 milligrams of CO2. And you might think that's such a small amount compared to the whole thing, because the whole volume is going to be like 7 grams, right? Of which we are using up 0.003 for CO2. But considering the rate at which we are increasing the amount of CO2 and the rate at which it is not being removed from the atmosphere, This can be problematic to the environment, and we should be considerate, or we should be concerned about it and consider things that we can do to alleviate the stress on our ecosystems. Now, trees love CO2. They use it as food, right? They do photosynthesis to turn CO2 and water into oxygen and glucose. So the trees are happy. Be a little less happy when we all go extinct, I guess, but for now, the trees are happy. All right, same situation with our lead problem here. So we'll say that the lead parts per billion, ironically, they all have the same letters in there, will equal the mass of lead divided by the mass total times a billion parts per billion. And again, same thing. What do I know? Well, I need to figure out the ppm limit here. So, oops, I don't know that. What am I doing? I do know the mass of lead in here because I have 4.5 micrograms of lead. I know the total mass of the water because I have its volume and its density. And then this is just a number. So we can just plug these numbers in as we go. So what is the mass of lead? It's going to be this divided by, we need to turn this all into the same units. So what I'm going to do is I'm going to change this from micrograms to just regular grams. I wrote a minus and it ended up like doing a horizontal slash there. So the good news, I guess, for me is that you don't really know which of my things that I'm mistakenly writing are Photoshop errors. I guess you could tell because I'm annoyed with it, and which are because I'm genuinely tired. All right, our volume, or not volume, but our mass down here is going to be the volume times the density. So I'm just going to write 300 milliliters. Grumble, grumble. Times 1.0 grams per milliliter. So we'll do that. So that'll give us our mass ratio, which we then multiply by 10 to the 9 parts per billion. So this would be 4.5 times 10 to the minus 6 divided by 300 times 1 is just 300 times 10 to the 9 parts per billion. So 1 times 10 to the 9. And I get 15.0 parts per billion. And that's the EPA limit. So if there are more than 15 parts per billion of lead in your water, it is considered not safe to consume. Now, that is an incredibly small amount of lead, which tells you just how obnoxious lead is in terms of biology. Like, it will bind to proteins. It can do stuff with enzymes. I'm sure that it interacts with your brain in some way and causes problems. It's just generally not good. If you want, you can read about how in ancient Rome and Greek times, lead, crystal, and stuff like that was considered very, very valuable, and that people would eat off of plates that were made of lead, and they considered it to have a very, like, dignified taste. That last part I'm not so sure about, if they actually consider, like, oh yeah, lead tastes great. My food tastes like lead. That makes me feel good. Because if that was true, then they were surely going insane, like, because of lead poisoning. But it's ancient civilization, so, like, who knows, right? It could be any number of things. But lead was definitely among them. One of the health concerns of that era. All right, we don't do 7.1 because it's chapter 7. I used to, and then I thought to myself, like, no, there's enough in this class. So that's it for chapter 6. There is a summary at the end here. Let's see here. So here's the chapter 6 summary. We'll put this on the screen here. So things that we covered, like, nobody really reads this, right? You can read it on your own if you'd like. So. Okay, so let me get chapter 3 out, and then we'll see if I actually want to do chapter 3. Because I have 15 minutes. That's the wrong chapter 3. I was like, that's a lot shorter than I expected. That's because I opened the 121 folder that I'd showed you those slides from before. This should have like 180 slides in it. 155. Yeah, it does. Okay. What can I do in 15 minutes? Yeah, we can do a little bit. Okay. So here we are. This is chapter 3. This is, from this point onward, entirely new. Everything in chapter 3, until we get to the very end, which will be like week 7 or 8, believe it or not, all totally new. So if you're watching this from the future, welcome. You're going to have questions. This is the new stuff. Ask me questions about quantum mechanics. Please, please, please do. This shit is weird, okay? And because it's new, we have now hit what I am calling the Aptitude Wall, which is I'm 161 student that I took 140 and I did really well. I've put 0 effort in this class because it's all review so far. Hi, it's chapter 3. And you just slam right into the wall because suddenly it's new shit and you have to actually pay attention, but you don't have the study habits developed yet because it's now week 4 and you've developed a pattern, right? I'm talking to you, you 40 people that aren't watching this video right now and are watching it later. I'm calling you out. Yeah, in a class of 50, I have 6 people watching here. So I'm calling you out, the other 44 students. Show up to these lectures. It's going to help you. And if you don't, ask me questions. Please ask me questions. Because look at these topics. What the fuck are any of these words, right? Except for the stuff at the bottom that you're familiar with, because that's going to be the 140 part. So this is the chapter that's going to screw you if you don't put in some effort and some time here. And I'm not saying this out of like harshness. I'm saying this as a warning. Every time I teach 161, I see people. This is where people shit the bed. Is chapter 3. Okay. Take this seriously. I cannot stress it enough. All right, let's get started. Chapter 3 is about electrons, and there is one thing that you can do to electrons that allows us to study them, and that is bombard them with light. So it behooves us to understand what light is. And you might think, well, light is just the thing that comes out of the light bulb or the screen, and that's a good starting point. But there's properties of light that we need to concern ourselves with. For example, what exactly is it? Light is this. Light is... Oops, it didn't advance. Light is an electromagnetic wave. An electromagnetic wave contains 2 parts to it, the electric field component and the magnetic field component. This is stuff that you'll study in physics when you talk about electric fields and magnetism and how they interfere with each other. When they are combined together, you create what is called a photon. Now, because it is a wave, it has wave-like properties. Those wave-like properties we're going to explain in just a little bit. Now, interestingly, a photon of light is considered to be a packet of information, like a small quantity of data. For instance, it's got an energy and a frequency and a wavelength to it and so on and so forth. But things that are particles should not be behaving like waves, right? A wave is a continuous thing. Woo, there's my wave. Whereas a particle would be discrete individual things. Light somehow is both of these things at the same time, which baffles and boggles our minds because we like to compartmentalize things into very convenient formulas and stuff, and light does not obey them. It obeys everything at once. And so what we're going to do is we're going to just have to accept that this is a thing, and we're going to call this the wave-particle duality of light. So light behaves like an oscillating wave, but it also exists in packets called photons. So it is both a stream of continuous energy, because it acts like a wave, but it is also not a stream of continuous energy. It is a stream of discrete energy in photons. Now, the confusion can arise because we are using crude tools relative to light to analyze light. We are trying to analyze something that is incredibly tiny. And thus, it looks weird to us. So in reality, it could just be particulate in nature, and we just can't discern it. We're going to treat it as if it has all the properties of both things. Particles, which means they have momentum, and waves, which means they have frequency and amplitude and stuff like that. This first section that we're going to talk about, we're going to look at the wave properties of light. Those are going to be important to us because they're going to measure properties like energy and frequency and what color the light is and so on. We're going to come back to the idea of particles and photons later on. Light is stupid fast. Light moves at a speed that is so fundamental to the universe, we've given it a letter. That letter is c. Here is its speed. 3 times 10 to the 8 meters per second. Now, this number is rounded. This has 3 significant figures. However, we've defined the speed of light to a very, very specific number. In fact, we have defined it so well that we have set up the meter around the speed of light. And here is the exact speed of light. 299,792,458. This is not rounded. We have defined the meter and the second around this number. So light moves exactly 299,792,458 meters in 1 second. By definition. That is stupid fast. Now, a practical application of this is if you see lightning. Lightning strikes will travel essentially instantaneously to your eye. The sound wave that results from the crashing of the electricity striking the ground moves roughly 340 meters a second. So you can determine how far away a lightning strike is by just counting the seconds, and every 3 seconds is about a kilometer. Now, that's just a sort of fun thing that you can do. But this number we're going to use, just rounded to 3 sig figs is probably enough. We're going to use this for anything involving light. All right. Now, any form of light, whether we consider it to be wave or particle, is going to operate at the velocity c. That means that our wave is going to go along like this. At a velocity of c meters per second. We're going to assign some terms to our wave based on whatever our length of this is. So we'll say that this is a 1 second worth of wave. All right. The first property we're going to talk about is the amplitude. The amplitude is the intensity of the wave. And there are no units for it. The reason that there are no units for amplitude is because we're going to see later that we can measure amplitude in a very interesting way based on number of photons, because waves should add together. And it turns out they do. We'll talk about that later. The next property that we're going to define is the length between any two identical points on the wave. So the two peaks up here will be some distance apart. Likewise, these two valleys will be some distance apart, and those will be the same distance. I could say the descending part of the wave, as it crosses through the baseline, some distance apart. And that distance is going to be the wavelength. The unit for wavelength is, or not the unit, but the variable for wavelength is lambda. Now, there is one more thing that we can treat as a property, and that's going to be shown on the next slide. How many wavelengths, so total wavelengths, so this would be a wavelength, are there per second? So if my wave is going, how many is it doing per second? That number is going to be, oh goodness, I didn't mean to click that. That number is going to be relevant to how much energy the wave contains. And that's called the frequency. And that's going to be on the next slide. Now, both amplitude and wavelength affect energy. The higher the amplitude, the more energy there is. You could think of this like waves crashing against the shore, waves of water. If the waves are very stout and tiny, and you're standing at the beach and you get hit by a tiny wave, it'll just lap at your feet. But if you have a tsunami where the wave is 10 meters tall and it hits you, you're going to regret standing on the beach. So the higher the amplitude, the more energy the wave carries. But what about the frequency? What about the wavelength? If one wave hit you every second versus 20 waves hitting you every second, the 20 waves would have more energy, right? Now, how would that be related to wavelength? Well, we need to actually look at that in a diagram here. So on the top, I have, well, first of all, we're going to assume that all of these are 1 second intervals. And so that this is the start at 0. So what I would do here is I would say, okay, I'm going to count top of my wave. So there's 1, and this would be 2 right here. So this top red wave has a frequency of 2 per second. The per second is called the hertz. You've probably heard of hertz in the form of your CPU has a specific processor speed. It's in gigahertz. It does some number of computations per second. We measure the frequency of a wave in per second. This wave down here would have a frequency of 1, 2, so 1, 2, 3, 4. This would be 4 per second, or 4 hertz. And then this one down here, we'll start at the bottom, I guess. 1, 2, 3, 4. This would be 5 hertz. Now, you're noticing that the wavelength for each of these is getting smaller and smaller and smaller and smaller. As the frequency, which has this variable nu, this is not a v for velocity, this is the Greek letter nu. As frequency increases, the wavelength decreases. How are the two things related to each other? If you multiply the frequency, which is in per second, times the wavelength, which is in meters, you get something in meters per second. What could that be? Guess what? It's the speed of light. So if I multiply frequency and wavelength together, I get the speed of light. And this is true for any photon. And that's where we're going to leave off. So if you found this confusing, be here on Tuesday. It's going to get worse. I guarantee it. I do want to thank everybody for coming out to the lecture. Please, 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 so essential. Chapter 3, we're here. We fear it. It's terrible. It's so long and confusing. Please ask me questions. I'm going to do my best to explain this. We're going to try and go slow, but I can't go too slow, or else we'll be in Chapter 3 until the end of the quarter, and we still have Chapters 4 and 5. So yeah, that's all I got. Quiz number 2 is due tonight. It will close tomorrow. Make sure you get that in by the deadline. Lab worksheet number 2 is due next week. Ask me questions about that in the Discord. I will be available all weekend. I will not be available tonight. I am out for the remainder of the night until probably much later. So I won't be able to address very many questions until probably 10 or 11 tonight. But if you have them, go ahead and drop them in the Discord or send me email. Happy to get to those when I can. Yeah, that's all I got. Have a wonderful weekend. Make sure you're preparing for the exam next week. Quiz number 6 will go up tonight, and we'll see you on Tuesday. Take care.